some particular deadline, some prediction should be given back, and your actuators, they will work according to that. So if you are interested to know more about these applications, you can go through this paper. This is the name of the paper. You just search in Google, you will get it. Okay, so this is the traditional applications that nowadays we are already using. On top of that, we have some existing and some futuristic frameworks that is coming. Those are coming into picture. One is this one. This is called machine graph. We generate a clinical model of a patient, and the idea is patient. I mean, the person will actually wear some wearable band or something. You have your smart watches, like, right? So that type of some wearable bands, and it will some sensing information will come to that band. That band actually will have some microcontroller or microprocessor embedded platform support, and there these patient data, whatever was accurate, based on that the model will predict some monitoring steps for the patient. It will basically constantly feed the patient with some health related information. Okay. Along with that, there is some initiative from Google. This is also very similar. That is based on that we should start from starting from taking one pill, and that will help us to get some nanoparticles which will detect and diagnose the disease. Okay. And the patient can use a wearable similar wristband to view readings coming from the nanoparticles. Not only when I'm telling the readings, it is not that just what is the just whatever readings the particles are accruing. Nothing like that. Based on those readings, there will be some prediction, and for that you have to go through that prediction step of your machine learning model, and after that the prediction results, those results will be shown in that wristband. Okay. Similarly, another initiative is this Entopsis, where this now through this nano engineering and machine learning, this medical conditions will be checked. So these are different initiatives, but why we have considered them in the same slide? Because you can understand that for all of them, the basic objective is same. You are actually getting some data from this wearable, getting some input in this wearable band. Wearable band means nothing but one embedded platform. There are some machine learning algorithm, prediction algorithm will go. I will tell why I'm just talking about the prediction. Why not the training part? The prediction algorithm will go on, and that will display, that will give some information to the person or the patient, whoever is wearing the band. So this is a very I mean works are going on in different directions, and these are very meaningful, important when we are talking about this type of out of hospital medical treatment. This type of trends are coming. Okay. So similarly, this is brand emotions, that is for emotion sensing. But so far, whatever this 1, 2, 3, 4, whatever we have talked about, those are related to medical data or medical health related support. Other than that, the fifth one, what we are going to discuss, analysis, that combines the weather forecast and the sensor data. So that is basically to improve the agriculture, to support some predictions, and to help the farmers. So that is there also, because in the farming field, there this sensor based data collection and their prediction. There also you cannot think of settling huge servers. There also you have to think about, because when you are thinking about farmers, they will be using some this agricultural plants, something that will be meaningful for agricultural plants. There also we need some smaller devices, smaller microcontroller based support, and this is another initiative where machine learning and embedded system, they are clubbing together to help to contribute in the improvement of agriculture. Another is patronics. Okay, this is related to robotics. So this is the first robotic mouse. So you can see that Tom and Jerry movement. Basically, the control. What will Tom do based on Jerry's steps, or what Jerry will do based on Tom's movement? Basically, now till now, this mouse part has been developed. So this is based on cat's movement or cat's reaction, how one autonomous mouse will actually take the next move. So this is of course this structure, this architecture is again developed in an embedded scenario. That means those predictions, the mouse will predict the next move based on the inputs coming from cat's movements. So there also, this is also the merging of this ML concept, and that was implemented in embedded scenario. So whatever we are talking, in spite of the fact we have seen yesterday huge layers, huge models and huge data, but still things are getting practical. Nowadays we have some practical implementations through which we can believe that okay, this embedded machine learning can be practical. But what is the general trend? General trend is that the the way deep learning became so much popular, that the trend is that you understand about the cloud computing, right? you, you have the idea about cloud computing. Is there anybody who doesn't understand what a cloud looks like? Can you tell me what a cloud looks like? Hello? Anybody?
Ma'am, cloud computing is when we send data to a large server somewhere else through a network, and the computation is done in the server, and the data is returned to us. So that's
Yes.
cloud computing.
Okay. So that means you have the why we are using, why we are pro to this cloud computing. We have the anticipation that in cloud, sorry, in cloud we have multiple servers connected. Okay, so there is no problem of computation platform support. That means there is no problem in terms of resource. The cloud works in pay as you go manner. That means I need more support. Okay, I'm paying you extra, give me the computation. So that is the concept of cloud. That's why machine learning was, the machine learning operations was first based on in the cloud scenario. Because there, if you want to, now you today you are planning to increase your number of layers, or you are planning to increase test or do your training on a larger data set. You may have some issues about memory, resource constraint. So in cloud, you do not think much about that. You just play the extra and you get the resources and you get your work done. But when we are talking about wearable applications, these will not be the case. Okay. First thing is that if you still think, okay, I am taking this sense, because wearable devices that should be connected to the patient's body, or the human who is actually activating the band and who is expecting the prediction. So you can think this way, okay, the let the band get attached to human body, the patient's body. The data we will collect through the sensor attached to the device, and then we will send the data to the cloud. Okay, and the whatever prediction, whatever the machine learning steps we have to do, we will do that in cloud. But the problem there is, whenever we are thinking about wireless connections, or for that this wearable device, that need to, you have to make some arrangement that your wearable application should always be connected to the cloud. Although always be connected to wireless connection, it will be always be connected to cloud. And to support that, it may happen because whatever you are doing, it's a small battery driven small devices. So that may drain the battery of your device too quickly. So before doing the actual prediction, maybe you have just collected data through the sensors, and just during the phase of transmission, your battery is getting drained. So you have no scope to actually get the prediction result back or check it back. So this is not a very meaningful solution when we are talking about wearable applications that always connect to the cloud. This may not happen. Another concern is a privacy concern. Though the fact is, all this, whoever you are coming from electronics and electrical background, you may think, okay, this wearable application, the power is a constraint, battery is a constraint that we accept, that we believe. But security, that I mean, why that may be a major issue. But yeah, I mean, I'm not going to this slide totally, but you can see the names here: Yahoo, eBay, Dropbox, Microsoft, Apple, whatever clouds at present you use, sooner or later, they have all gone through some kind of data leakages. Okay, and these data leakages, you may go through the list. I'm not, because it will take time. And this is the list is given up to 2017, 18, and even in 2021, this year, you can have, there is huge number of records just within this first 4 5 months. There are huge number of, huge billion of records that got that got compromised. Okay. When the this Apple Cloud, they cannot uh, protect their own data, that their user ID, data, password, and many more, many images. So you can understand, when you are talking about this wearable device, you are sending your personal data. You have to take into account that there is some possibility of this data hacks or data leakages in cloud. Okay. And on top of that, just this is one example to show you why security is important, especially in the Western world. Till now, maybe we think, nowadays there is some concern, and there is some consciousness, I must say. But in Western world, this consciousness is much more. You can think, this is one example I have given. This is a huge database, in terms of medical data. Medical data is a very critical component in terms of security. So this huge number of people, their data got compromised. Okay, and for that, just why I have kept this slide is to show you the amount. This is the huge amount the company has to pay just to mitigate this issue, just to handle this issue. So when we are talking about privacy or data leakage in cloud, so, and most of the cases, this leakages, these breaches, they got they are left unnoticed. They are never discovered until and unless some lawsuit was filed related to that, and huge money to be transferred to handle this issue. So when we are talking about privacy, of course, huge monetary involvement and there, and that way the security nowadays, data security is itself a very critical concern. So that means when we are talking about wearable device, you are getting your sensor data, and you want to process on that. You want to process some machine learning algorithm on that and get the insight of that. What is the option? Now, sending the cloud, as we have discussed, you are sending raw data here, and you are doing both the training and inference. For that, to do that only for the inference, it may happen while you are getting this classification result. Till then, you are, your battery, you are losing in terms of your battery, and due to the scarcity of resources, this solution is not be very much meaningful. Okay. Now come to the other solution, what we are talking about, and nowadays research is going on in this direction. This embedded machine learning. That means we know that training is very costly part, and in real time, in run time, we are not doing the training. That means, so what is the solution? We can focus on the inference only, because training, we know, as we have discussed yesterday, you remember, to do that training for in CNN, we have to first layer, we have to check the and get the classifications. We have to check whether it is getting as per our actual prediction or not. If not, we have to go layers of layers. We have to go layers by layers, and then we have to do back propagation. We have to adjust those weights, and then we have to finalize the weights. So it is huge computation. So that we know at this stage we cannot support with our embedded scenario. But what about the inference only? In inference, we have already fixed the weights. So then this is just maybe one shot, we can tell. Yes. In that one shot, that we can actually use those weights that we have that we have actually in that information we have got from this training phase, and that we have continued in cloud, and we are using, we are passing, maybe you are storing that weight features in your wearable device. That means you have some processor, that processor is having some memory there, maybe you have stored that weight feature. I'm just telling we will see much more how it actually occurs in the coming examples, but just a basic idea, you are storing that weight values, and with those weight values you are doing this inference. So we are checking only that much is manageable or not in our present embedded scenario. So where is the gap? Now see, to do that, for recent real-time networks, maybe now you can see these names. So whatever we have discussed yesterday, you know what are the layer requirement, what are the steps requirement of VGG, you know about GoogleNet, you know about ResNet, MobNet, and MSC1 version of that. So you know all this, you have some idea about all these DNN architectures. What are the processing, background processing going on or required for these DNN architectures, you have the idea. Now I'm telling you this data that to implement that, okay, what the number of this is, we are we are considering the requirement to implement that. So we are considering the requirement in terms of GOPS or TOPS. If someone do not know, GOPS means gigabillion operations per second, whereas TOPS means trillions or tera operations per second. So basically with this we are measuring the throughput. Okay. Now throughput means how many, you can, as the name suggests, you can think in this way, the operations per second. We are getting some idea how much operations we are doing per second, and what is the requirement for this neural network, and for our existing embedded devices. You know that in these devices they only work in some milliwatt or microwatt scenario, microwatt support. So where we need around 100 TOPS or 1 TOPS level, what we have so few tens or hundreds GOPS per watt. So there is from this graph also you can see there is a huge gap. Especially this gap is specially for, you can say this dots. This dot means it is not right. This dot means this is for always on devices. Okay, always on devices, or always on, I should write always on applications. Applications, and this one here based on your mobile based applications, that is not always on. So when we are going for some always on applications, this requirement, this operations per requirement per second requirement is high. And given our embedded device, the power features, the energy consumption features, efficiency features, there is a huge gap till now. Okay. So we will talk about this more, and how we can mitigate these issues when we are talking about this always applications, like in your embedded wearable devices. You are going to do some predictions for machine learning operations. So for that, what we need to handle, we need to handle some interplay between the applications. So we have to check what kind of application we can take into account. It is not that all type of applications with all layers we can actually map to our embedded scenario. We are, our literature doesn't support that. Our existing power requirement, energy support, everything, that is, with that it is not possible. So we will first identify what type of applications we can actually do. Next, what type of algorithmic optimization. So we will modify the network topology a bit. We will tweak in the weight end, we will tweak in the feature selection end, and many more we will discuss step by step. Also, we will improve the processing architectures a bit and circuits a bit. So we will come back to this one by one. Maybe throughout this semester, basically we will discuss, we will take one solutions, one options from this direction. Okay. Now before that, I will come back to this slide once again. We will talk about this when we are talking about operations per second, or Tera operation, GOPS, whatever these terms we are telling, we are primarily measuring this throughput. Now, to understand that how we are measuring the throughput, we have to understand a bit basic about our embedded architecture. What we have when we are talking about one embedded platform, what type of support we are getting. Okay. Now, just as of now, just see whatever written here. I will explain them step by step. So whenever we calculate this type of throughput, maybe this one, there's a tera operations per second. What we take into consideration, we take into consideration number of MAC units into frequency of MAC operations into 2. Now, what we mean by this MAC operation? This is multiply and accumulate. Okay. Now, throughput, maybe for computer science, electronics, electrical, you are coming from different backgrounds. So, throughput for different applications, for different scenario, you have computed it in different ways. Why I am choosing this, just specifically these expressions. Why we are talking here, we are introducing here this concept of multiply and accumulate. To understand this, I think now you can understand that very easily, because you can remember whatever we have discussed yesterday. We have discussed that the most costly operation in CNN, we have talked about pooling, we have talked about normalization, etc., etc. We have talked many things. But the most costly operation that we have talked about is convolution, right? So that means when you are doing this type of multiplication, convolution means nothing but you have one filter and you have this input matrix, you are doing this multiplication. You are multiplying and accumulating. And finally, you are getting one some final output matrix. Maybe some dimension reduction, etc. Many things are there. But the basic operation that you are doing, it is basically this multiply and accumulate. Okay, that means you are multiplying just in a simple way. You can think, you can see here what we mean by this multiply and accumulate. If you have, this is coming from existing, this is the instruction supported by ARM processor, where if you want to do this kind of operation, you want to do some multiplication and then you want to do one addition, that you can do in a straightforward way with one instruction support that is called MLA. That's why I have taken this example actually. See, what this MLA tells you, MLA, you are specifying one destination. Basically, you are not specifying when you are writing this multiplication code in your this type of ARM processor. There is a mapping to this instruction. I will come to it how this mapping is happening. But as of now, just think whenever you are writing this multiplication, that mult do this multiplication. Then this is getting mapped to in ARM processor. It is getting mapped to this MLA instruction. Now see the structure of this MLA instruction is MLA destination, operand 1, operand 2, accumulator. Okay. So if that is the case, basically what you are doing this. This is your R1 into R2. These are your parameters. Okay. You are doing R1 into R2, and then you are adding that to R3. Some previous result you are adding that to R3, and you are storing that to R0. Okay. This is your instruction. See, this is exactly what you are doing when you are thinking about any kind of matrix multiplication. You need to do some multiplication and then you have to do some addition. That is your purpose. So it is good if you have one processor and there you just write this, do this multiplication, and it is mapping that to a particular instruction, and that instruction is working for you. So that's why we have taken this example of this multiply and accumulate, because this is very meaningful for our case. Okay. So the key idea is that if you have some support from your processor, that the type of operation you are trying to execute, that is directly getting mapped to some instruction, and the instruction is doing everything for you. Of course, there will be some instruction level optimizations, and with that you can get some performance optimization, better performance, better throughput, everything you can get if this instruction, particular instruction, is getting supported by your processor. Okay. And while we have some, because why I'm telling this, if you go back to this, you can see there are different options of embedded processors. GPU, FPGA, even CPU, ASIC, you have some NPU, that is neural network related processing unit. So you have this everything, and these processors, they have different flavors, different advantages. But the key idea is the operation that you want to do, if you can map it efficiently to this processor, then your work is sorted. I mean, you can expect a better output. You can expect a better performance. So that's why if you are getting this kind of instruction support, that will be advantageous in terms of implementing your I mean embedded in terms of implementing, or in terms of realizing your machine learning application in embedded scenario. Okay. Is this part clear? Is it clear?
Yes, ma'am.
Is it clear for everybody? Okay. So if it is clear, then tell me one thing. How many of you, maybe those who have already done some embedded our foundation course or embedded software design validation, maybe they have the idea. But others who are coming from that, I mean, not maybe they have not done any architecture course, computer architecture course. Do you really understand that what happens when you are writing some program? Maybe you all of you, I assume that all of you have written some C code, right? C code you have already written. So when you are writing this instructions in this C code form, actually at the back end, how your platform is supporting, or what is the contribution of your platform or your processor. So I don't know how many of you, I mean, really know, or have you ever done this type of course, or if you know, that is fine, no issues. If not, I will share you. Okay, first let me tell you something about embedded system, and I will share you two lectures. Okay, that this part we actually teach it. If you think about like this, one simple C code. Okay, this is a simple C code. Maybe this is calculating GCD calculation. I think you all know how we can compute GCD by pen and paper mathematically. Now, when you are writing a code, how your processor is actually executing this simple C code. So that is step by step. It is given there. This is my lecture. So I will share it by today or tomorrow. So in next week's class, when you come here, I will request all of you, those who, especially those who have no idea about this, just go through those lectures once. So that will clear your understanding when I am writing anything. What is the challenge of when I am writing in C code? Let's say I am writing any int a plus b, c is equal to a plus b, d is equal to a minus b. These type of small C codes. What is the challenge? How it is actually executing in your system, in your processor. Okay, that part will be clear, because if that is clear for a general purpose processor, you can, whatever we will be discussing next day, it will be easy for you to understand that what are the challenges or what are the solutions we are providing when we are talking about embedded scenario. Okay, so I will share those links. Please go through them. Okay. Before that, a bit, maybe this is also a repetition for those who have done this embedded system or embedded software related courses. But for a general introduction, when we are talking about one embedded system, an embedded system is basically a controller, a dedicated function within a large mechanical or electrical system. Okay. Now you can think about this Google nanoparticle or that wearable band, whatever we have mentioned. Maybe that band you can think as a whole system. Inside that, you have some computation unit, and some sensor is giving input. So here also you can see the same thing. You can think about that sensor, the example we have taken, that sensor as our medical sensor that is attached to your band. That band is collecting data, and it is giving data to this computation unit. Now this computer may be a single, here the example is shown as multiple computation units. So these computation units, what they are doing, what is they are important for? They are taking this sensor based data and they are doing this machine learning related computation, this prediction in this computation unit. And then maybe there is some display. In the display, that they are showing some deduction that okay, this there is a possibility, what is the probability of that this patient is infected with this disease, etc. So that means this is, if you now think, if you keep that example in mind, you can understand this embedded controller, basically this computing unit who is basically doing the prediction within this embedded platform, is basically supporting the need of your embedded machine learning. Okay. Now, again, if you again come back to this definition, this application is a part of real-time computing. What do we mean by real-time computing? You have some, predefined deadline. So, deadline bound. The prediction result you are expecting within a particular time. It is not that you have the data was collected 10 hours back and after 10 hours it is okay to give it back to the result. 10 hours is also fine. I'm not telling that deadline. This is one idea that when I'm talking about something real time computing, it is not that something instantly you have to give the output. No, the output maybe there is a predefined deadline. That deadline may be 2 minutes, 2 seconds, 2 microseconds, or maybe 20 hours. If 20 hours is the deadline, then you have to meet that deadline too. So real time, if someone, after doing any embedded course, if someone asks you what do you mean by real time computing, never tell that something, some result you are expecting in, I mean, immediately. That is not the concept. Concept is deadline bound. Whatever deadline you are deciding, you have to meet the deadline. Next one, this is single function. Okay. Tightly constrained, of course, as at least one constraint today we have mentioned about the power. You have to work within this microwatt, milliwatt scenario. So tightly constrained. As we proceed, we will see some more constraints. Okay. And reactive and real time. Reactive means whenever this sensor is actually scheduled, when that sensor will actually fetch the data, whenever it is fetching the data, your computation, these blocks are active, because once the data is there, the new data is there, fresh data is there, based on that, this prediction part they need to compute. Okay, because it is for constant monitoring. So when we are thinking about embedded system, or we are developing one machine learning, I mean embedded ML controller, this type of wearable device, what we are expecting, that this device, of course, you can understand in terms of battery, in terms of power, it is tightly constrained. It is single function. It is not that that device is doing so many things, multiple things, like in your system, in your laptop. You are now listening lectures, you are opening PPTs, you are presenting something. So there are multiple, you are running code, so there are multiple functions. But when you are talking about this embedded systems, these wearable devices, you are having this single function requirement. So I hope now you understood that what are the characteristics of this embedded system. And when these characteristics are there, that will obviously influence our machine learning realization. Now, when we are talking about this embedded system, of course, we are concerned about the processor. So this processors means, okay, before that, we can come here. So processors, the what is the, I mean, the, when we are talking about processors, they look like this. You can think these are the components. You have some data path, control path, some program memory, data memory, and ALU. I am not going step by step what does it mean of these components, because the lecture I will share there, you will find everything. Otherwise, it will be a repetition and it will unnecessary, it will kill our time. Just one point I want to focus about this general ALU. What do we mean by ALU? ALU means the full form is arithmetic logic unit. Maybe most of you know this thing. And these ALUs, they are composed of, maybe you have some modules added, you have some module multiplier, maybe some subtractor, etc. So ALU is supporting the modules by which you can actually run, I mean actually realize your instructions. That means when you are writing in your C code, just think about the C code. You are writing add AB. That means somehow there is some code for add, and with this code your processor is understanding, okay, now I have to add. What will be my inputs to this addition? This whatever stored in this A and B. Okay, so it will be fetching this data and it will be passing these information to this ALU. And this ALU module, adders, multipliers, or whatever is, I hope you all gone through the C operators when you have written the instructions. Whatever operations you can think of, you have to realize them whatever block that is supported by this ALU. So whatever ALU you have, that is coming from your processor. The processor is giving the support of your ALU, and this ALU is giving the support of your basic blocks. So whatever your instructions are there, that instructions should get mapped to this ALU, and then ALU will compute this adder for you. Okay. So I think if there is some doubt, maybe you can ask me next day, because today I will give another concept. You first go through for the whole. Here in this slide you will having you will be having this example, and then how it is actually getting mapped to ALU, and actually how this execution is taking place. So I will share that video, share that audio lecture. So just go through that. If you have any doubts, ask me next day. I will hear it out. And that is, this is same for what I have taught actually in the last class in ESDV. So if some of you are there, if you are common, you are taking the both the subjects, so you may skip that. Okay. And while going through this discussion, you can have that there are general purpose three types of processors, like this name suggests. So that is basically based on whatever support you are getting in this ALU. If you are getting just a particular support for a particular instruction, then your ALU is restricted and your implementation is also kind of restricted. Okay. So how this mapping takes place, you can go through that lecture, but now I want to give you one important concept. Like, okay. So you can come back here. So here we are actually answering the question, which embedded processor is suitable for machine learning. Okay. So in this case, we have talked about that whatever instruction or whatever ALU support is there, based on that, actually we can get the what we are getting, what we can implement. Whatever my ALU is supporting, my processor is supporting, what type of instructions, like if my processor is supporting this add or underlying adder, then only I can implement this add, or sub. If some mapping is there in my arithmetic logic unit, then only I can implement this sub. This is not fully true. Okay. That we will take this example of one instruction set computer. Now with this, in this computer, we have just one instruction. This is the structure of this instruction. Okay. What it is telling? It is telling you have, this is the name of the instruction, this sublect A, B, C, and it is taking some values B stored in the memory of B. This is a B, those are the memory locations, and they are performing this subtraction and they are storing that to this value memory. So what does it mean? We are basically in, if you think about the ALU of this particular computer, you have just one operation supported there, that is one subtraction unit, nothing else, because you need to only compute this subtraction, and that subtraction result is getting stored to this mem B. This means the memory location defined by this value B, or memory location defined by this value. So that means, let's consider you have one computer that is basically supporting one single instruction. That ALU is just supporting one single, what to say, block, that is the subtraction. So with that, can you actually develop any kind of operations? The answer is yes, you can do it. You can go go back and you can check for this add, not, basic operations. You can take take your C operators as an example, and you can check for this how there are different steps, the multiple steps, and by handling them in an intelligent way, you can actually implement all this kind of instructions. So in this class, we do not have much time to actually explain how all the instructions we are actually realizing by this one instruction set computer. One example I can show you, maybe this addition. Okay. Here you are doing this, you have only this operation, this mem b minus mem a and mem. And you are storing that value to mem b. So now you take this example, that means az, where maybe in your memory location A, you have stored some value, maybe say 5. Okay. And your memory location B, you have stored some value that is called 3. That is maybe 3. Anything you random value you can take. Doesn't matter. Now for the Z, it is storing 0. It is by default, it is storing 0. Now for this first one, what you are doing? You are in Z, you are basically storing Z minus A. Z minus A means the value is 0 minus A, 5. Okay. Next subject instruction, what it is telling? ZB. That means here you are storing to your B, you are storing B minus Z. Okay. Now this B minus Z is B minus 0 cancelled out, B plus 5. Okay. B means B location, whatever you have in your memory location B plus 5. Now in memory location B, you are having 3. That means it is giving you 3 plus 5 and the result is 8. Okay. So that way basically you are performing this 5 plus 3, this addition operation, just by rearranging few this single instruction. You are having just one single instruction in this computer, nothing else. But you have to implement all this operations. And at the last, for this last instruction, what it is doing? It is flushing. That means it is setting again the Z, this value to 0, because it will be again used, that may be used for the next subsequent operations. So why I'm telling this example, why I'm explaining this example, that means it is whatever you are doing, it is not always based on your platform. Whenever you are taking one algorithm, you have mapped it to some sequence of instruction, maybe some code you have written for that. Now, whenever you are mapping that to a particular computer, of course, it is what performance you will get. What it will be. Now you can understand, like if in here you have to actually execute 3 subject instructions. So your timing will be 3 into maybe say S. Maybe S is the timing required for the executing one subject instruction. Now, if we are thinking about one processor, maybe our modern processors that directly support one adder module. That means you are not developing, not using multiple instructions. Just one instruction you are writing add, and your computer underlying processor is actually executing that add for you. And this add maybe you are doing in one clock cycle or one machine cycle, we can tell. Whereas to do this type of subject instruction, add with the subject instruction, you are using basically 3 machine cycles and so on. There are multiple operations, and for them you have to use multiple number of instructions, and that will incur huge overhead in terms of clock cycles, machine cycles. So why I'm telling all these examples? Because to make you understand, whatever you are choosing underlying your platform, whatever instructions that platform is supporting, that is controlling what performance you will get, and not only performance, some other the throughput, what power, etc., etc. Everything will be governed by that, will be controlled by that. This is called the concept of instruction set architecture. Whatever instruction set your processor, your underlying platform is supporting to you, based on that, you have some limitation. And that limitation is also holding us to implement, to realize some application in embedded scenario with this real time requirement, or refraining us to choosing some application in embedded scenario. So it is everything, because in underlying, of course, we are not going to use one instruction set computer. We are going to some application specific computer that will help us, what we have told, mentioned, to support efficiently, to implement efficiently these type of instructions. Okay. So that is the main catch, that what, when we are trying to find out, when we are talking about the, I will map my ML algorithm to some embedded platform. First thing is that what type of platform I am going to choose. I'm going to choose that type of platform. Of course, first of all, it will satisfy my embedded requirement. That platform, that embedded processor, that should can be integrated with my wearable band device. That cannot be so huge. That cannot be, I mean, very costly, because then people will not buy my wearable bands. So these requirements will be there. And also the main requirement is that what type of these instructions and how efficiently in the underlying platform is supporting these instructions, that will in turn, I mean, give me the support whether I can actually meet this real time requirement or not. Okay. So if you actually use this type of one, you have the option to use this type of one instruction set computer. But if you do for one simple instruction, you have to realize multiple instructions. Doing so, you will may miss the deadline. Maybe it is not time effective. It is not performance effective, the performance that you want. Whereas you may choose some recent modified but costly processor, embedded processor, that may be supporting some this type of this other multiplier direct modules, direct instructions, and those implementations are very fast for them. So of course that will help you to realize the realize and to also meet your real-time need when you are mapping your embedded machine learning algorithm in your embedded processor scenario. Okay. Do you have any question? Tell me. Do you have any question? I hope, I mean, what I expect, there are multiple questions. Okay. So tell me, what do you want me to repeat some part, or is everything clear? Anybody? There is no answer. Can you hear me? Hello?
Yes, ma'am.
Can you? Okay, good. You can hear me, right? So is this part clear? That how your underlying processor choice can actually affect the processing time of implementation? What is the concept of instruction? I mean, how instructions supported by your processor is actually controlling the improvement of your any algorithm algorithm implementation. Is this part clear? What I will suggest, you go to that the I will whatever link I will share, the audio lecture link, that we will go through. Then you go through this today's lecture and then ask me if you have any doubt. Okay. Just one point I want to add here. Okay. The question we are, trying to answer today, that what type of processor will be suitable for machine learning scenario. One answer maybe you have understood, I hope, that some processor that is supporting this type of multiply and accumulate functionality in an efficient way. Okay, that can that can implement this multiply and accumulate part in an efficient way, but because that we will be doing repeatedly. Okay, now to do that, okay, before that, how many of you, most of you have done some DSP courses, right? Signal processing.
Yes, ma'am.
You have done. So you have the concept of this Fourier transform, and the signal in signal processing. One typical requirement is the this type of multiplication, FFT multiplication. So maybe today we do not have much time, but next day we will start from here when we are talking about this. What type of processors are useful when we are talking about machine learning scenario. We will talk about this kind of DSP processors, digital signal processing, the related processors. Why? Because the reason is that in this signal processing applications, they typically perform some sophisticated mathematical operations. Specifically, we will focus on that FFT multiplication. And we will see for this DSP processors, there are some the idea is something like that. I'm just telling it today. Next day we will explain it in a more detailed way. The idea is we have this type of, we have to do like in our matrix multiplication in our convolution. We have to constantly we have to do this type of repeated multiplication and then additions, right? Now, while the first thing is that the direct implementation is that will allocate an array in memory, like you will store these values. Maybe you all know array implementation. So that array implementation means you are storing these values somewhere in some memory, consecutive memory locations. Each time once input sample arrives, there will be some related multiplication. Okay, and then it will move each element in the array to the next higher location. If you are doing so, there is harm and there is a possibility of wasting the memory. But when we are talking about embedded system, embedded devices, embedded platforms, we have some restrictions in terms of memory. That's why how these DSP processors, they actually modify this storage of memory, how we can arrange this memory in a better way, in a circular buffer way, that will help us to prevent this type of wastage of memory. So this is one typical example of which type of processor will be meaningful when we are talking about machine learning. We will take this in detail from next day onwards. But before that, if you just go through today's discussion, because this is very important, do not skip it, and the link I will share. So whoever they are not having some idea about this processor based implementation, how your code or how your implementation is getting mapped to processor, I think that will help. So after that, if you have any question, next day I will sort it out. Okay, I will answer your questions, but that lecture you should go through. Okay, anything else? Any question? Nothing? No question? Have you understood this part? At least a bit. Have you got the idea? Yes or no?
Yes.
Yes, ma'am.
Okay. Okay. Then maybe we can wrap up this class for today. Next day we will start again. We will discuss again about the why this type of DSP processor or what type of processor will be specifically important when we are talking about this machine learning implementation. Specifically here it is told one term, NPU. So what does it mean? So we will discuss all the things next. Okay. Thank you.